Swayam Prabha. Digital India. Educated India.
Now we are going to learn about this very useful tool called projection operator, which is going to make our life much simpler than what it is for the rest of the course. What had we discussed the previous day? Symmetry adapted linear combinations, right? What are the problems we discussed? BH2, CH4, and that's it, right? So in CH4 what we did is, how did we get the symmetry adapted linear combinations? First part is easy, right? You take the atomic orbitals of the pendant atoms, make a reducible representation, break it down into constituent irreducible representations. That much is fine. But then how did we generate the reducible, how did we generate the SLCs? So we did it by inspection, isn't it? We did it essentially by inspection, right? Now that is not going to really work when you try to tackle bigger, larger systems. So we need something which will make our life a little easier, and that something is, as we learned today, projection operator. So we want to eliminate that. What we want really is SLC for dummies. I'll say that this is the formula, use it, we will use it and we will get the result. Alright. So, but to make anything for dummies, somebody somewhere has to do a lot of behind the screen, beyond the spotlight work. Otherwise, you cannot generate things that would be only for dummies. Okay. We want to develop a machinery by which one should be able to generate the SLCs without having to worry too much. Okay, that's what we'll do today. We'll develop what are called the projection operators. What do projection operators do? Projection operators project, as the name suggests, right? Projection operator should project. What should it project? As we will see, if a projection operator is going to take any function and it is going to project parts of the function that belong to a certain symmetry species, and thereby we are going to generate the SLCs. Alright, and to do this, again we use the power of great orthogonality theorem. In today's discussion I am going to follow Cotton's book, but you might find it more useful to read this from Bishop's book. So the treatment that we had done earlier, in Bishop's book, if you take the trouble of reading it, actually I think it's easier to understand. In Cotton's book, once again, it's a little bit of hand waving is there, but let's go ahead. Let us consider a set of functions which belong to an L dimensional irreducible representation. Okay. So let us say phi 1, phi 2, phi 3. Let us put a general identifier phi t, etc., phi L. Oops, phi L. All right. And we are saying that they jointly form the basis for some irreducible representation. If it is the ith irreducible representation, right, we are used to this notation, ith irreducible representation. So let me just to remember that these functions all form the basis of the ith irreducible representation, let me also put the superscript I on every function. I hope that's not very difficult, right? So I have L number of functions, phi 1i, phi 2i, etc., up to phi li, which jointly form a basis for the ith irreducible representation of our point group. So far so good? Okay. What happens when I perform a symmetry operation on any one of these functions. I will take the general one phi t I and make a symmetry operation, operate on it. What should you get? Okay, when are you going to get plus minus phi t I? When the representation is one dimensional, right? Or in some special case where it turns out by some accident that out of the L representations one is by itself, but that is not going to happen, at least not for all the symmetry operations. For one symmetry operation it may be possible. Okay. So what would be then the most general expression? It would be a linear combination, exactly. And if I may remind you what happened, think of the xy vectors in say C3V point group. What happens when C3 operates on x and y, or on x for example? C3 is z axis, right? This is xy, this is C3. So I operate C3, 120-degree rotation. So what does x become? What is Rx? Ax plus by is right. What is A, what is B? Since I have told you 120 degrees, you should be able to tell me what is A and what is B. And what is cos 120? Minus half x. So x becomes Rx, right? C3x is equal to minus half x, then plus root 3 by 2 y. Similarly, you can work out what is C3y. That will also be linear combination. Root 3 by 2 x minus half y, isn't it? Right? So you know what the matrix is going to look like. Okay. So in general, it is going to become a linear combination. Okay. If you remember our discussion of function space, when you perform the symmetry operation, what happens is the length does not change, right? But since the angle changes, the components along the original orthonormal set that defines the space, those components are going to change, right? Initially, y component of x was 0, x component of x is 1. Now in the transformed vectors, x component, y component both are non-zero, isn't it? So let me write a general summation. Will you allow me to write it like this? Sum over S phi S I gamma R S T I. Okay, it is a little different from what we are used to seeing. We always write the coefficient first and the function later, right? But see, it's a linear sum. Does it suppose x is equal to Rx? Rx is equal to what do you say? C3x. What is C3x in C3V? Minus half x plus root 3 by 2 y. Okay, it will look a little odd, but I am perfectly right if I write it is x into half plus y into root 3 by 2. Who will stop me from writing it? Right? I am perfectly justified if I write the coefficient second and the function first. It is just that we are more used to writing the coefficient first. I am sorry? Yes, but this is only a row of the matrix. If you take the gamma R ST, right? Right? So I have only written a row. And so next, if I can write R hat phi t plus 1 I, then you will get another one. So on and so forth, I can generate the whole matrix. Instead of the whole matrix, I am only focusing on phi t I and its transformed avatar. Alright, so I am not considering the full matrix, and I am perfectly fine in a linear combination if I write the coefficient second. Of course, when we write something in an odd manner, there must be some reason for it. Here also I have a reason for writing it in an unusual manner, and the reason will become clear very soon. Are we okay with this? Are we okay with this? Can I go ahead? Right? So now, the reason why I have written it on the right hand side is that because I want to eliminate it. That is very clear. Okay. How will I eliminate it? It is a matrix element of the transformation matrix. I can multiply it by its complex conjugate, sum over all R, and then Our great orthogonality theorem will allow me to write a single number in place of that sum. What is great orthogonality theorem? You take a matrix element of the transformation matrix, multiply it by the complex conjugate of any element of the same transformation matrix, or of another transformation matrix is also okay actually, right, and sum over all R. Then what you get is 8h divided by square root of Lij del Ij del S dash del T dash. Kronecker delta, multiplication of 3 Kronecker deltas, which tells us that these matrix elements behave as a set of orthonormal vectors. Remember great orthogonality theorem? We are going to derive great orthogonality theorem at the end of it. So let's come back to what we are doing now. What I will do is I will multiply this left hand side and right hand side by say gamma of R for S dash T dash J. Yes. Okay, what is R? R is a symmetry operation. Okay. What is gamma? If I write nothing else, gamma is the irreducible representation. But if I write gamma of R, right, okay, let me write it like this, gamma of R with superscript I. That is the transformation matrix corresponding to R in the ith irreducible representation. And then when I write ST as a subscript, then it means the ST element of that transformation matrix. Understood? Huh? So R symmetry operation, gamma I is the ith irreducible representation, gamma R I is the transformation matrix corresponding to R in the ith irreducible representation, gamma R I ST is the ST element, I do not know what it is called, ST element or STth element or STth element, whatever it is, you understand what I mean, the element of that transformation matrix. Okay. Now may I proceed? Now see this STI, these are all general indices, isn't it? Are they not all general indices? I have not said that S equal to 5 or S equal to 2 or anything. They are general indices. They can take different values, all the possible values that are there. How many values of I will be there? Number of classes. Very good. That we learned from great orthogonality theorem, isn't it? Number of irreducible representations is equal to the number of classes. What about S and T? What will be the limiting value of S and T? L. Dimensionality. Dimension, not order. Dimensionality of the ith irreducible representation will be the limiting value of S and T. Okay. Does S always have to be equal to T? No, it can be anything. You can have say 1, 2 element, 3, 5 element, whatever. All I am saying is the maximum value of S is Li, maximum value of T is also Li. Only maximum values are defined. Okay. So you have understood our ST and I's? Surely? Question? Have you understood what is I, what is S, what is T, and what are the limits? It's important to understand that. But now when I just write gamma R S dash T dash J, what I am essentially saying is that S dash T dash J, these have some specific value. Okay, I am taking one of all the different possible matrix elements, okay, and I am multiplying both sides by that. So this is a specific matrix element. So you can write 1, 3 and 5 here, for example. Okay. These are not general indices, these are specific indices, all right. And to make it more fun, I am going to put a star on it, right, because this is our star, this is what will help us construct the projection operator. Okay. So we should give it due credit and put a star, while not forgetting the star means complex conjugate. But most of the time we are not going to use the star, as you will see. Okay. Fine. So multiply, what do you get on the left hand side? This multiplied by r hat phi t I is equal to sum over s phi s I gamma of r s t I, this is annoying, gamma of r s dash t dash j star. Okay, I have just multiplied both the sides by some element. Okay, how will I get Kronecker delta? First of all, you have to sum, don't forget that. Kronecker delta will not come just like that. Only when you sum over all the symmetry operations will the right hand side start looking like the left hand side of great orthogonality theorem, isn't it? So what you need to do is, you need to sum over r gamma r s dash t dash j star r phi t I will give you. I hope nobody has an objection if I take this out and I put the summation here. I can do that, right? Gamma r s t I, then gamma r s dash t dash j star. Okay. See if that is all right or not. All right. What is this equal to? H by square root of Li Lj del Ij del S dash del Tt dash, and I am myself impressed that I have been able to write three deltas that look all different. All the deltas are different from each other, but that is not intentional. Okay, so how do I simplify life a little more? You put I equal to j, specific value, put s equal to s dash, specific value, put t equal to t dash, specific value. What does the right side hand side become then? This part, h by square root of Li Lj, square root of Lj Lj. So it is h by Lj. Okay, right, left hand side becomes sum over r gamma of r s dash t dash j star r hat. Now see, in whatever I have written so far, nothing has changed, isn't it? By putting this Kronecker delta, nothing has changed in whatever I have written so far. You notice that? Now the change will come. Here it is already in terms of some specific s dash, some specific t dash. So up to r hat, nothing has changed. Also, what is this? This whole thing is like an operator, isn't it? R is a symmetry operation and you are multiplying it by some matrix element and then summing it over all R. So this whole thing is like an operator. So this is the mother of projection operator. Projection operator is going to come from here. Okay. What should I write here? Phi t dash j. Okay, is equal to, this becomes then phi s dash j h by Li Lj, right. This is a mistake that I always make and then later I get kind of confused. Phi s dash j h by Lj, right. What happened to the summation? There was sum over s. Sum over r is gone anyway, right? sum over R product of the matrix elements has been replaced by your H by root over Lij, del Ij, del S dash dash, del Td dash. That summation over R is gone, and then what I have done is I have put S equal to S dash, T equal to T dash, I equal to J. So out of this summation, the only term that survives is when S is equal to S dash. That's why I have written phi S dash J. Whichever is your question answered. What is the question? Left hand side, because I want to make this Kronecker delta is equal to 1. So when will this delta Tt dash become equal to 1? When I put T equal to T dash, that's what I have done. T dash is a specific value, T is a general value. Okay, just let me finish this up. So what do you have on the left hand side? If I write Lj divided by H, sum over R, gamma R, S dash T dash J, okay, star of that, R hat operating on phi T dash J is equal to phi S dash J. What has happened? What just happened? I have taken this operator, maybe I will use a pencil. I have taken this operator here, made it operate, right? This is also within the operator, sorry. I have taken this operator, made it operate on a wave function, and this is why we have to substitute I equal to J, a wave function which is a basis for the jth representation, and I have generated another wave function which is also the basis of the same representation. I want to work within the same representation, that is why. Understand what's happened? You take some function, see this operation that I have written, this operation is a property of what?
How are they linearly independent?
What?
How are they linearly independent?
What do you mean, what does this have to do with linear independence?
Basis should be, the components of the basis should be linearly independent.
Yes. So what I am doing is, I am operating this on some arbitrary wave function, and I am projecting the, okay, I understand. This can be a linear combination also. You take an orthonormal basis function and you take linear combination of the basis elements, that also forms a basis. Right? So let us say we are working with a linear combination. Well, we are going to do that. So if this is a linear combination, you can project out the component. If this is a component, then you can actually construct the linear combination. Let us wait until we come to the example. But this is the operator. All right? Fine. Tell me, whose property is this? S dash T dash, right? So it relates these two. So this thing is called the projection operator. In fact, it is called the complete projection operator, and we are not going to use it. Let me write it once again. And let me tell you something, we don't really care about the Li by H as well. Even though in the definition everywhere Li by H is written, we don't really care about the Li by H, that is only a number. As we will see, that number is irrelevant, because in any case whatever SALC we generate, we are going to use the, we have to normalize it. So the number doesn't matter. So I won't even write the number, even though that is going to be at variance with what is written in all the textbooks.